This is lecture 7 of Machine Learning and Bayesian Inference. In the last lecture, I got most of the way to finishing off the derivation, at least as far as I'm going to take it, of the learning algorithm for support vector machines. I covered it as far as formulating the maximum margin algorithm in a space that's been extended using basis functions, or now using a kernel function. And where I left it was with the thought that it may be the case that even after you map into a larger space, you still can't separate your classes using a linear classifier. So the last step in this particular piece of development is to take that bull by the horns and modify the formulation so that we can still formulate a sensible training algorithm in that case. So that's what I want to do first today, and then I'm going to move on and talk a little bit about how you might apply algorithms like this in practice, and about some of the practical difficulties that can arise. But let's start with finishing off support vector machines. So the slide here is really just summarising where we've got to. We only looked at the linearly separable case, and now we want to move slightly beyond that. The diagram here is just summarising the maximum margin classifier, where we'd shown that we can essentially regard the alpha parameters rather than the weights themselves as the output of the training algorithm, and we'd expect most of those to be 0 because they're only non-zero for ones that are closest to the decision boundary. Well, things aren't going to be that neat, but we still get most of the kind of nice outcome that we get from the maximum margin algorithm when we now take this final step. So what are we going to do? Okay. Well, we have to think first a little bit about what happens in this scenario when an example is misclassified. This diagram shows precisely that situation, where we have this one example which is misclassified. It's on the wrong side of the decision boundary. All that means is that our product, in this case, if the training example that's on the wrong side of the boundary is x prime, y prime, the product of y prime f of x prime is now going to be negative. Okay, that's what happens when you have a labelled example that's on the wrong side of the decision boundary. Okay, that follows from all the stuff that I laid out in the last lecture. Now that's going to be negative, so we can't impose the constraint anymore that we did with the maximum margin classifier, which was that y prime f of x prime would have had to have been greater than or equal to 1. So we need to be able to relax that constraint, but we want to relax it, if you like, as little as possible. Okay, the whole point here is we may not be able to divide our training examples linearly, so we want to reformulate this constraint optimization problem to allow that, but in some sense to still get as close as it can to maximizing some idea of the margin between the class labelled +1 and the class labelled -1. And to do that, we introduce for each training example a slack variable. So the ith training example has an ith slack variable psi of I, or psi sub I. We force those to be non-negative, and now instead of trying to constrain y prime f of x prime to be greater than or equal to 1, we constrain it to be greater than or equal to 1 minus its slack variable. So, the fundamental idea now is, as summarized at the bottom of the slide here. Although we now have a training example x prime, y prime that's on the wrong side of the decision boundary, so we can't constrain y prime f of x prime to be greater than or equal to 1, we can constrain it instead to be greater than or equal to 1 minus its slack variable. And then we force the slack variables to be non-negative but also small. Now, when we do that, we're just modifying the previous constrained optimization problem a little bit to take these slack variables into account. For the maximum margin classifier, the problem was as in the first box here. Okay, we were minimizing the length of the weight vector in such a way that we would force a margin between the decision boundary and each example, and we do that across the whole training set. Now we modify the optimization problem in such a way that we're still going to try and maximize some conception of the margin, so this is the same, but we're going to add a second element to the function that we're trying to minimize, which is this guy here, which tries to control the amount by which we misclassify our training examples. Okay, so the sum here is trying to keep the slack variables small, and we've introduced a new parameter c, which is a hyperparameter that we get to set that controls the trade-off between maximizing the margin and controlling the misclassification. And the constraints that we now have try to keep the slack variables non-negative, or force the slack variables to be non-negative, and use them as suggested to allow one or more of the training examples to be on the wrong side of the decision boundary. Okay, so that's the reformulation that allows this to happen. But it is important, in fact completely critical, that we've introduced a new parameter c, which we now potentially have to control for. Now, if you carry through all of the same kind of mathematics that was in the last lecture, if you apply the Cruciker-Tucker conditions to that version of the optimization problem, you find that you still get the same insights in terms of being able to recast the learning algorithm as choosing the alpha values, the Lagrange multipliers, rather than the weight vector, and you still get the same form for the solution, and when you plug it in you still get all of the same behavior in terms of introducing a kernel function, because you can use that to take place of the inner product between the capital phi vectors. And that gives you the constrained optimization problem that you solve, that constitutes the training algorithm here. And as I've already mentioned, I'm not going to go into the details of how you do that numerically using numerical methods, but I will give you here the fundamental paper that discusses sequential minimal optimization, which is kind of the basic way of implementing this constrained optimization problem in order to train a support vector machine. This is just an illustration on some straightforward training data, although slightly less straightforward, I guess, than the stuff that we've used till now in terms of toy problems. What I have here is two classes that are two interlocking spirals, and in fact they're two noisy interlocking spirals. At the bottom of this slide, on the left, we have the result of training a support vector machine using the RBF kernel mentioned at the end of the last lecture, with this new C parameter set to 10, and with sigma squared, which was the width of the RBF kernel. If you wind back to that slide and just look at the definition, you find it there. And you can see that it's pretty successful in learning this data. It divides the two classes quite nicely. You can see there is a black line denoting the decision boundary that you end up with in this case. And you can see that around the blue dots, which denote one of the classes, the output of the SVM is strongly positive, and where the red dots denoting the second class live, you can see that the output of the SVM is strongly negative. Once you get away from where the data is, we have this area of grey, so it's not really committing one way or the other, which is possibly what you would hope for. Now, I will come back to this example a little bit later, because once again, and I can't emphasize this enough, the choice of the hyperparameters, the C and the sigma squared, is critical. And we're going to look later at just how critical that is when we talk about how you might actually choose them in practice. On the bottom right of this slide, we have the outcome of using a polynomial kernel of degree 5. Again, if you wind back a little, the definition of the polynomial kernel is a few slides back. And again, I've used c equals 10, and here we can see we have much less success. The decision boundary, you can see, makes a valiant effort initially to divide the classes on the outer parts of the spirals, but then it rather fails in dividing the classes once they get kind of wrapped up towards the center. So, an example here of the importance, potentially, of a good choice of kernel. I suspect at this point that you won't mind too much if I now change the subject a little and give you a little bit less in terms of the hard and potentially unfamiliar maths. The next thing I want to talk about in this course is some of the difficulties and subtleties that can arise in practice when you try to do supervised learning. And there are a small number of specific things that I want to flag here. The first is that quite often in practice, even in the straightforward case of two-class pattern classification, you will come across the situation where you have more examples in one class than in the other. And this can have an effect, both in terms of how best to train your classifier, and certainly in how you then assess it afterwards. The obvious measure of performance in this case is not necessarily the best one. I've been using so far as a measure of generalization performance simply the probability of making an error. It will quickly become apparent that you have to be a little bit careful just using that if your classes are unbalanced, by which I mean you're likely to see one class more than the other. The second important point in terms of doing this in practice is that, as I've hinted several times, choice of hyperparameters could be absolutely critical. This can be the difference between getting a very, very successful outcome and getting essentially nothing that's usable. So we need to look at ways in which we might choose these hyperparameters in practice. The third thing is that we need to be extremely careful if we're interested, for example, in developing new supervised learning algorithms, in making a claim that our algorithm is better than anyone else's. It is very tempting to do a quick experiment, find out that your shiny new algorithm in a quickly done experiment gets some kind of better measure of performance than the ones you compare it with, and then conclude that it's better. It's not as straightforward as that. If you want to be convincing when making such claims, you have to be rather more careful, and you have to do rather more extensive experimentation. So that's what I want to talk about now, and at the risk of getting ranty, I'll try and avoid that. There are quite a few machine learning commandments in this part of the course, And the reason for that is that so many people get this so wrong. It is not at all unusual to see publications in which people do not take the care that one might hope that they would in setting out the experimental results and the analysis of the performance of their learning algorithm after it's been applied. So let's start with a fairly basic reprise of what I set out in artificial intelligence last year when I talked about what supervised learning looks like, because there was an important thing that I missed out, at least practically speaking. When I talked about supervised learning last year, I talked obviously about wanting to come up with a classifier that would take an attribute vector, a feature vector, X, and map it to a label. And I denoted that classifier, I think, just in terms of the weights that you pick. And now I'm just extending that idea slightly. So now the classifier that we end up with after training depends on theta, and theta contains both the weights that we get as the output of our training algorithm and the hyperparameters, any other parameters that are associated with that algorithm, but are clearly separate and have a different purpose to the weights that we're using to choose some underlying function. Now, to keep this sort of notationally simple, I'll stick to the idea of two-class classification with the classes labelled plus and minus 1. When I spoke about this last year, I also gave you a diagram a bit like this, where we have the learner, which is taking a training sequence, S, and is picking our parameters so that the classifier we get is a function of S. Okay, L here is the learning algorithm. But the box that I left out last year is this one. I left out the blood, sweat and tears box. Now, what do I mean by this? What I mean by this is that it's sort of a dirty little secret of the machine learning world, that you don't just pick up a learning method, turn the handle, and expect great results to come out. There tends to be experimentation involved. In fact, when you're faced with real data, that experimentation ought to include trying a whole bunch of different methods. And even in our new world of deep learning, the chances are that there's going to be blood, sweat and tears involved simply in choosing an appropriate architecture for the problem at hand. If it's an SVM that you want to use, the blood, sweat and tears comes in terms of the lengths that you may have to go to choose the hyperparameters correctly, and the lengths that you may have to go to convincingly show that your SVM has superior performance to any number of other techniques that you could have tried. Okay, so no matter which way you cut it, the blood, sweat and tears box is actually an important one if you do this kind of stuff in practice, okay, using real data of any kind. So, we've already come across one commandment, which was thou shalt try a simple method. In fact, you should be trying lots. So I'm expanding that one. You should try many simple methods and possibly many complicated ones as well when you do this in practice. But I'm going to add now, as the first kind of important thing that needs to be clarified here, I shall use an appropriate measure of performance. And the reason that we need to flag this is that the performance measure that's been used so far is not always going to be the appropriate one. But before I talk about that, I have to talk about something even more fundamental, and it's this. If you want to measure how well your algorithm, your learning method is doing, then you have to assess it using data that it didn't see during the training process. This is an absolute golden rule for the supervised learning context. You will only ever have a finite amount of data available that you can use to train your system. That data has to be used wisely, and the real golden rule here is that you will have to split it in some way into one set that is your actual training set. Okay, you have an original set which is all the data you have available, but you're going to have to split that into the training set you're actually going to use and some that you keep aside for doing assessment. S prime here is what you use to measure the performance of your algorithm after training. And although it seems obvious that you should split your available data in this way, and that you should only evaluate your system on stuff that it's never seen before, people still get this wrong. Okay, it was particularly prevalent in the early days of machine learning and neural nets, but things have improved since then. But you will still sometimes see people not adhering to this golden rule. If you use data during training, which you then later use during the assessment of the performance of your system, you are going to tend to bias your results towards the positive, okay, towards being better than they really are. So this is definitely to be avoided. How do you choose the size of these two sets? Well, trial and error. Quite often you see 10 or 20% as rules of thumb used for the size of the test set that you hold out, and 80 or 90% as being the size of the training data, but this will be moderated by how much training data you actually have to play with. You don't want to make your actual training set too small. The question then is, how do you use that held out data to assess the performance of your trained classifier? Okay, so if you have the classifier and it's already been trained, how do you then use S prime, your held out set, to assess its performance? Well, so far I've been talking simply in terms of using the probability of error as your measure of performance. That's very, very easy to estimate, okay, if you have some held out training data. Here we have an estimate of the probability of error. Now, I here is just the function that counts 1 when the predicate in brackets is true and 0 when the predicate in brackets is false. This is called the indicator function. The thing in the sum here then, for an ith held out example, okay, an ith example in the test set S prime, this will be 1 when your classifier predicts the corresponding label correctly, and a 0 when it doesn't. So the sum counts the number of errors that are made on your test set, and dividing by the size of the test set gives you an estimate of the probability of error. This is exactly like estimating the probability that a bias coin comes up heads by flipping it m prime times and counting how many heads you see, and then dividing one by the other. Okay, so this is a very straightforward way of using your held out test set to estimate the probability that your trained classifier makes an error. The probability of error estimated in this way is often called the accuracy. However, if your data is not balanced, this can be a misleading thing to do. In the case that you have unbalanced data, if one class is much more likely to occur than another, I fall back on the usual example of medical diagnosis in this case. If you're trying to diagnose some condition, then most people who turn up will not have it. That means that if you simply always predict that the person who's turned up doesn't have the condition, you will do quite well in accuracy terms. if the condition you're interested in only appears in 1% of the population, and your rule for diagnosing it says always diagnose the patient as not having the condition, then you will be right 99% of the time and you'll get an accuracy of around 99%, or 0.99. That's a very good accuracy, but it's a lousy classifier because it never catches anyone who has the condition. So, we need more subtle measures of error, particularly for the case where classes are imbalanced. So, let's say that we have a set that has m plus positive examples and m minus negative examples. We can now make some definitions that allow us to write down some more subtle measures of performance. There shouldn't be anything controversial on this slide. The true positives are, as you might reasonably expect, the number of examples in the set of interest that are labelled 1, and which your classifier also labels as 1. Okay? Your classifier says they're positive, and they are positive. Hence, this is the number of true positives, p+. The false positives, this shouldn't come as any surprise, are the ones that are actually labelled negative, but that your classifier counts as being positive. Okay? It labels them as positive, but falsely. This is p-. And the definitions for the true negatives and the false negatives are similar. Now that allows you to define a whole bunch of alternative performance measures. I will only list these. I won't be giving examples of when you might want to use them and when you might not. That is problem dependent. The important take-home message from this slide is that depending on where your priorities lie in terms of assessing the performance of a supervised learning system, one or more of these performance measures may be more appropriate to you than just the straight accuracy measure. Okay, so these are standard measures of performance that are applicable under different circumstances. If you want to get into the detail of how you might assess classifiers in practice, there's also something called the receiver operating characteristic curve, which is what you get if you plot sensitivity versus the false positive rate while varying some parameter of the algorithm. But I'm not going to have time to go into any more detail on that way of assessing performance. If you are interested in summary measures for the case where you have unbalanced data, then there are two specific measures that are of interest to you. And really, if you have unbalanced data and you just want to give a summary measure of the performance of your trained classifier, then you should be using one of these or both instead of accuracy. Okay, we have the Matthews correlation coefficient and the F1 score, both of which are defined in terms of the quantities introduced on the last couple of slides. Okay, so this is important. If your data is unbalanced, don't report performance in terms of accuracy for the reasons that I've just given. You would use one of these instead because these correct for the imbalance in the data. The last thing I want to do in today's lecture is just give you an illustration of how important hyperparameter choice is. And here is my advice for how you handle hyperparameters, again, if you train supervised learners in practice. First point, don't just use the default ones. If you ever use a machine learning library, the chances are that it will have hyperparameters associated with the method you're using, and it will set some as default if you don't specify otherwise. These are almost certainly not good parameters for your specific data. Okay, so doing that may actually get you a classifier that works moderately well, but unless you are more sophisticated in your choice of those hyperparameters, the chances are you won't be getting the best performance that you possibly could. The second point here is don't use an unprincipled formula that claims to tell you what hyperparameters to use. I've been doing this a very long time and I've never seen one that you would really trust in practice, although they do occasionally get proposed. The third point here is don't expect hyperparameter choice to happen by clicking the Learn button for your third-party piece of supervised learning software and just hoping that it does something sensible. Unless you know what it's doing in terms of choosing hyperparameters, well, you don't really know what's going on. For all you know, it's just using some default parameters. Unless you know exactly what's going on behind the scenes, you may, again, be ending up with suboptimal performance. And finally, the really important thing, you have to choose them carefully and give them specific values, or integrate them out. Now, what does that mean? Okay, well, that's a more Bayesian way of dealing with hyperparameters, which I'm going to come back to later. Okay, so one way is essentially to do a similar kind of trick as we used with the introduction of the Bayes optimal classifier, which essentially integrates over all possible functions that could be the proper functional relationship for your data. We can do a kind of similar thing in the Bayesian context with hyperparameters and just kind of average over all possibilities weighted according to how probable they are in the light of the data. That's a less common way of dealing with them, so I'm not going to talk about that until a little bit later on in the course. The key point here is you need to choose these things carefully, and now I'm going to give you an illustration of exactly how critical this can be. This is the example that I showed earlier in the lecture for a support vector machine being trained to solve this problem with two interlocking spirals forming the two classes. On this slide, I have C, the parameter that tries to enforce a minimal amount of misclassification, set to 1, and it's fixed. And across these four examples, I'm altering the other hyperparameter, which is the width of the radial basis function kernel, sigma squared. The outcome, the way to interpret this, the outcomes of training with these different sets of hyperparameters, is that the output of the SVM classifier is strongly positive for white shade on the diagram and strongly negative for black shade on the diagram, and the intervening levels of grey tell you what's happening between the two extremes. So on the top left example, hopefully what you can see here, there is still a black line denoting the actual decision boundary. But you can see that that black line is very closely fit around one class, okay? Namely the one that is corresponding to negative output, the red dots. In fact, if you look very closely at this, you'll see that it's in fact going around those dots in some places. The other class, as you can see, each blue dot is surrounded very closely by an area where the output of the SVM classifier is strongly positive. But essentially the classifier is learning each of these examples individually. Okay, it's giving an output that's positive or negative. It's doing that appropriately for the individual examples. But once you get even a very small distance away from one of those examples, it's classifying it at somewhere around 0. Okay, so this is going to have essentially no ability to generalize. If you now give it a point that's not one of those training points, hopefully you can see that it's just going to give you an output somewhere around 0, and it's not really going to give you any kind of consistent form of generalization. If we move to the top right example here, where we've made the width of the RBF kernel slightly greater, we've gone from 0.001 to 0.01, we can see that we're getting something much more sensible. Okay, this is looking like quite a good choice of hyperparameters. The decision boundary in the form of the black line seems to be dividing those examples quite nicely. There's a smooth light area around the blue examples and a smooth black area around the red examples. That suggests that if we now, for example, pop in a new blue example, it's probably going to get classified correctly. The generalization here looks quite good. If we go another step, which is the lower left diagram, now we're making the hyperparameter for the RBF kernel width too big. We've got quite nice performance here at the outer parts of the spiral, but you can see that for the inner parts of the spiral everything just falls apart. We can't actually learn on the right scale there, where these examples are getting very close together. At this point we're going to generalize quite well for examples that are in the outer part of the spirals, but horribly badly for anything closer to the center. And if we go to the lower left diagram, then things are even worse. Here the decision boundary is just giving one class above the center of the diagram and another class below it, and now we're not learning to do anything of much use at all. So that's keeping C fixed to 1 and varying the width of the RBF kernel. Okay. What happens if we go the other way? Let's keep the RBF kernel at its nice setting, which from here is 0.01, and vary C. Well, we can make a bunch of similar observations. The lower left diagram here looks like the sweet spot again. That looks pretty good. Notice that here we've got C equals 1 and sigma squared is 0.01. Here we've got C is 10 and sigma squared is 0.01. And in both cases they're doing quite well by the looks of it. Okay, so there may be some leeway in terms of the hyperparameter choice where we can vary them a bit and still be in the kind of sweet spot for good performance. But the important point here still is that for inappropriate values of C, for wildly inappropriate values of C, the performance completely falls to pieces. Okay, and that's the case certainly in the top left. Once again, we've got a situation where you wouldn't really expect much in the way of generalization here, because although the decision boundary seems to be picking out one of the classes reasonably well, certainly on the outer edges of the spirals, the background is a fairly uniform grey, so there isn't much commitment either way when we put new examples in and try and classify them. On the top right, it's a similar story, and on the bottom right, once again, we're moving away from good generalization in the sense that the decision boundary still looks quite sensible, and we're getting some commitment to one class or the other, but less so than in the bottom left diagram. Okay, so this is only 2 hyperparameters. You may have many, many more, depending on the learning method that you're using and the way in which you're setting things up. Even with RBFs, if you're using a even with SVMs, if you're using a non-RBF kernel, there may be more parameters than just the one that you have here, the sigma squared. And if you have more hyperparameters, then clearly the space you need to search over to find a good set can be much bigger. Okay, but the important take-home message from these last two slides is that even here, with only two hyperparameters and with a relatively straightforward toy training and test set, the choice of the hyperparameters can be absolutely critical. Okay, and that's going to be even more so if you do this with real data and more than two hyperparameters. So what I want to do in the next lecture is initially look at how we might systematically search for hyperparameters in practice, and after that I'll go on to talk about comparing one classifier with another.